Unit 5.2 Linear Factors and Zeros. The objective of this unit is to analyze the factor form. So what a factor form is, in this polynomial function of x equal to a factor times another factor. This is what we call a factor form. And then we're going to learn how to write a polynomial function from its zeros. You have to know the following three concepts before we can start the unit. First, linear factor. Second, zero and zero multiplicity. And the last one is factor theorem. To understand linear factor, we have to know what a factor is first. So what exactly is a factor? Let me give an example. So 6 is equal to 3 times 2. So 3 and 2 are factors of 6. So let's apply this concept to understand what a linear factor is. Let me give you an example. X plus 1 times x plus 2 is equal to x squared plus 3x plus 2. So if you think about this is a 3 times 2 equal to 6. So we know these two are factors of these polynomial expressions. So we call these two are factors of these polynomial functions. The reason we call this linear because the power of these things, the power of this variable is 1. That's why we call it a linear factor. So if you want to find factors of polynomial function, you have to do the factoring, which we cover in the last unit. Let me give an example. So writing a polynomial in factor form. So the first thing you would like to do is to find the biggest common factor of these polynomial functions. So the common factor you can find from these three terms is x, and the greatest common factor is also x for these three terms, the greatest common factor. So once you have x as the common factor, you extract it out like this, so you have a new expression right now. Then we can make use of the sum of factors to change these polynomial expression into a factor form. Once we get this done, we know x minus 5 and x plus 3 and x are factors, or I would say are linear factors of this polynomial function. Now that we understand what a linear factor is, the next concept we're going to learn is zero. So what exactly is a zero? The definition of zero is the value of x when the polynomial function p of x equals 0. So here are the steps to find the zeros of a polynomial function. So we use the example that I gave to you in the last PowerPoint slide, which is 3x to the third power minus 2x squared minus 15x. We change these expressions into factor form. This is the factor form. So we have three linear factors, x, x minus 5, and x plus 3. So these three are the linear factors. So in order to find 0, we just set all these linear factors into, we set all these linear factors equal to 0. So x equals 0, and then x minus 5 equals 0, and then x plus 3 equal to 0. Then we solve for x. In this case, x is equal to 5 and x equal to negative 3. So let me change color of the pen to highlight it for you. So right here, the 0, 5, and 3, the negative 3 are the zeros of this polynomial expression. In the last PowerPoint slide, I showed you the steps of how to find the zeros of the polynomial functions. In this PowerPoint slide, I'm going to show you how to graph them. So zeros in the graph. I'm going to use the same example we did in the last PowerPoint. And so the zeros are 0, 5, and -3. So we're going to graph it here. 0, 5, 1, 2, 3, 4, 5, and -3 right here. So let me label them. -3, 0, and 5 right here. So all these zeros help us to graph the polynomial function in a more accurate manner. So from unit 5.1 we know the leading terms here. This is the leading term of the polynomial function. We determine the end behavior and the turning points of the polynomial functions. So the leading term a, x, n, and in this case we have x to the third power. So the a is going to be 1 and the n is 3. So a is a positive number, 3 is an odd number. So these two pieces of information will tell you the end behavior of this polynomial function is going to be down and up. So in the graph it's going to be down and it's going to be up right here. The next piece of information that you can get from the leading term is the n powers. Because the n power is equal to 3, the greatest number of turning points is going to be equal to 3 minus 1, which is equal to 2. So we have 2 turning points in between this. So, but we have to pass through all these zeros. So the graph is going to be like this, pass through. I'm sorry, it's not that smooth, but you got the idea. So path here. Alright. So far what we have done in this unit is you're given a polynomial function and then they ask you, for example, something like that, and then they ask you to change it to factor form. It's going to be in terms of like the linear factors, and then based on that you find the zeros and then we graph them. That's what we've done so far. The next things that we're gonna do is actually doing the reverse. When I say reverse, that means I'm going to give you the zeros, and from the zeros you're going back to get the polynomial function. That's what we're gonna do in this part. So here's an example. So you're given 3 zeros, -2, 2, and 3. Based on this, we can change it back to the linear factors of each 0. If 0 is -2, the linear factor is going to be x plus 2. And if the 0 is a 2, the linear factor is going to be x minus 2. And the last one, if the 0 is 3, the linear factor is x minus 3. So the next things, you can do the FOIL on these two first, which you end up getting this expressions, and then you do the distribution. So you're going to do this one, and this one for the first expression. The next one, I'm going to use different color to show it to you. So how about blue? So the next one is going to be the constant 2 times x squared times minus 5x times plus 6, which give you this. And based on this too, we use the distributive property again. So we're going to do this 2x. I mean 2 times x squared, 2 times minus 5x, 2 times plus 6. So you end up getting this. The same thing apply for this one. So we're going to have x times x squared times minus 5x. This is distribution. Then you end up getting all this. After you get all these terms, you just simplify. Then you're going to have the polynomial function that you're looking for, which has the zeros of these three. The next concept that we are going to learn is the multiplicity of a polynomial function. So the multiplicity of the polynomial function will help us graph the polynomial function in a more accurate manner. Let me show you this example. You are given a quadratic polynomial function in standard form. First, you're going to convert this in factor form, which give you three factors here, three linear factors. So this one is the first linear factors, this is the second linear factors, and this is the third linear factors. Based on these three linear factors, we can find the zeros. Okay, let me show you the process. So since the first linear factor is x plus 2, and the second linear factor is x minus 2, and the third one is x minus 3, all we need to do is just set them up to equal to 0 and solve for x. So the zero is going to be negative 2 for the first linear factor. The zeros for the next one is going to be 2, and the last zero is going to be 3. If you pay attention to these three linear factors, you know there's a difference between this one and the other two. The difference is, for the first one, the power is 2, and that's what we call it has a zero of multiplicity 2. The other two, the power is 1 and 1, and we call them a zero of multiplicity 1. Now that we know negative 2 is a zero of multiplicity 2, okay, I highlight it for you, negative 2, multiplicity 2, and the zeros 2 and 3 is a zero of multiplicity 1. So how does multiplicity affect the graph of the polynomial functions? Whenever you have a multiplicity of 2, the graph bounds. Okay, I'll show you what does it mean by bounds. And for multiplicity of 1, the graph will go through. Let's put everything together so we can draw the graph. First, let's take a look at the leading terms right here, because it determines the end behavior and the number of the turning points. So x to the 4th power, if you take a look at the form in axn to the n power, that means a in this case is 1, the leading coefficient 1, so n is 4. So a is a positive number and 4 is an even number, so we know the ending behavior is going to be up and up. So it's going to be something like this, up and up. The next thing is the number of the turning points. Since it's n is equal to 4, we know the greatest number of turning points is going to be equal to n minus 1. So in this case, it's going to be 4 minus 1 equal to 3, or it could be 1. I don't know for sure, we'll check. And here we know the zeros are -2, so I put the -2 right here, and then I have 2, so I put 2 right here, and then I have 3, I put 3 right here. So these are the zeros. So one more time, -2, 2, and 3. So right now we know -2 is a zero of multiplicity of 2, so it will bounce. When I say it bounce, we go like this. Okay, and for 2 and 3, because the multiplicity is 1, so it's going to be going through. Since it's going up, so we're going to have this. Oh, please. Since 2 and 3 we go through, we're going to end up something like this. And we know there are 3 turning points. So if you join everything together, you're going to end up getting a graph like this. Of course, later on we know this one, the y-intercept is going to be 24 from the function itself. The last concept that we are going to learn is factor theorem. That's basically refer back to the start of the unit when we talk about factors. Take a look. When we start looking at factors, we look from a product perspective. For right now, we look at factors from a quotient or division perspective. In other words, if you look at the factor from a division perspective, as long as the remainder right here equal to 0, then we know the divisor 2 and 3 are gonna be the factors of 6. Similarly, if you have a polynomial function like this one, and it's divided by the divisor x minus 3, which give you the quotient of 2x plus 1. Forget the operations here. As long as the remainder equal to 0, we know the divisor x minus 3 here and the quotient 2x plus 1 have to be the factors of these quadratic expressions. That's what factor theorems is all about. Simply put, according to the factor theorem, x minus 3 is a factor of 2x squared minus 5x minus 3 is because 3 is a 0. So basically, when you put back 0 into this function, you know it's gonna be equal to, look at that. You simplify the whole thing, it's gonna be equal to 0.